Hello! We've just done the reindeer show, so I gave myself little coral antlers, but it's not really appropriate for this lesson. This is an IGCSE lesson about pressure in liquids. Let's get going. I've got a little specification point explanation for you, which I don't usually do. This is what we're learning today. For your exam, you would need to describe qualitatively, that means not using numbers, how pressure beneath the surface of a liquid changes with depth and density of the liquid. And you'd also need to recall and use this equation, which is how pressure changes beneath the surface of a liquid. So we'll talk about that in a bit. First of all, I want you to try these little puzzles, please. You've got 3 pictures here of a plastic water bottle, let's say, that's had 3 holes stabbed in it. So all these 3 bottles are identical, but different things are happening in each one. Only one of them is the correct scenario. So if you poured water into a plastic bottle, you could try this after to see. Would the very bottom hole shoot out water very far, the middle hole shoot out water not quite as far, and the top hole shoot out water just kind of falling next to the bottle the least far? Would the top one shoot out the furthest and the bottom one not shoot out as far? Or would they all shoot out and the streams meet at the same point? Very pleased on Facebook to see there are loads of different answers to this going on, which is always a good sign that you've asked a good question in teaching. Most important question is number 2. Why do you think that? So which one do you think's right, A, B or C? And why do you reckon? And then if you're done with that, how do you think the diagram would change if we used this bottle instead? So it's the same height as the other bottles, but it's much wider, it's a much bigger bottle. Have you decided? I'm just looking for my favourite liquid to demonstrate something to you. So unusual. Can't find it. I got it out yesterday for this lesson. Maybe it'll turn up as I'm going. Okay, have you got an answer for me? The answer is, well, this is a big clue here. Pressure in liquids increases with depth. So the further down you go, the more pressure is experienced. So the answer was A, because the water right at the bottom is obviously the deepest down, so it's shooting out the most because it's under the most pressure. And then the middle one is under less pressure and the top one is under even less pressure. And that is what this equation tells us, right? So if you imagine air pressure, we haven't really talked about this yet, but what air pressure is just particles of air colliding with your body. So for your exam, you would need to know that air particles, they're pretty far apart, generally speaking. They're not bonded together, so they're free to move wherever they like. But yeah, they are bashing into your body and obviously everything else. And that's what air pressure is. And we're basically living at the bottom of a sea of air. So air pressure increases with depth as well, right? We're right at the bottom where the air pressure is nice and high. If you go up to Mount Everest, there's not as many air particles, so there's not as many collisions with your body, so air pressure is lower, so it's not good for humans. And yeah, it's just the same with liquid, she says, stabbing her PowerPoint. Here we go. It's not even worth it. It's just the principle of the thing because I made it. My computer has frozen, I think. Oh well, I'll show you this slide and it might jump away in a sec. Here is, yeah, it did. Oh no. Here you go. Look, I had this fantastic demonstration of how pressure in a liquid is different to pressure in a gas, because in a liquid the particles are much, much closer together. Wow, my computer is just very tired. You can do it, buddy. That's it. That's literally it. It's just the particles in a liquid are much closer together, and so the pressure in a liquid is higher with more collisions with whatever is under the sea, but it also does get deeper. The deeper you go, the more the pressure increases. Okay, and yeah, if you spotted this equation on the previous sheet, you knew what this meant because this is the equation for the change in pressure beneath the surface of a liquid. So little triangle here means change in pressure. People on Facebook yesterday were saying this looks like Elvish, but a little triangle is a lovely quick way of writing change in. So change in P means change in pressure equals, so the change in pressure from, say, like the top of a lake to the bottom of a lake is equal to, careful, that's not a P, that means density. You remember we've done a lesson on density already, so that's the symbol rho. The density of the liquid times little g times the change in height. So in this case, height would be the depth, right? It would be like whether you were 0 meters below or 2 meters or 3 meters. We've already covered what little g means, so I'm not going to go into it in loads of detail, because if you've seen previous lessons, you know this by now, but little g is basically how much gravity is pulling down on things. And on planet Earth, gravity is pulling down with a force of 9.8 newtons, capital N for newtons, that's what measures force, per kilogram. So for every one, if there's like 1 kilogram bag of sugar on Earth, it's getting pulled on with a force of 9.8 newtons, okay? On the moon, it's different, it's like 1.6. So a bag of sugar that was 1 kilogram on the moon would be getting pulled on with a force of 1.6 newtons. But if the thing we're talking about is on planet Earth, which it usually is, they might get tricksy in the exam, then little g is always going to equal 9.8 newtons per kilogram, okay? You can also call it the acceleration due to gravity. So really, we're only really thinking about if the situation is on Earth, the difference between the pressure in a liquid at the surface and the pressure like 2 meters below or whatever, that difference only depends on the density of the liquid and the change in depth. Whew, I think you're ready for my fun times quiz. So I'm going to show you some containers of water, and I want you to tell me if they're experiencing more or less or the same water pressure as it does in this tank here. So we've just got a rectangular tank of water. It's 1 meter deep. It's 0.5 meter across. It's called tank A. Tank A is not going to change throughout all these examples. There's a tadpole in it. Don't worry, it's fine. It's having a lovely time, but it's right at the bottom of the tank, okay, of tank A. So I'm going to show you different tanks, and you tell me if you think that the tadpole in the other tank is experiencing more, less, or the same amount of pressure. So here we have a tadpole in a much narrower tank. This tank is only 0.5 meter wide, but it's still 1 meter high. The tadpole's in the same position at the bottom of the tank. Is that tadpole experiencing more pressure, less pressure, or the same amount of pressure as the tadpole in tank A? The answer is, it's the same amount of pressure, right? Because it's the same depth below the water as the tadpole in tank A. And we're only looking at the differences in depth or the differences in the density of the liquid. So it would be the same amount of pressure. What about this one? This time, the second tank is exactly the same as tank A, except the tadpole is floating in the middle of the tank, not on the bottom of the tank. Same amount of pressure as tank A, less pressure or more pressure? The answer is less. It's now experiencing less pressure because the depth has changed, right? The depth is more in tank A. Now the tadpole is less deep down, so that the height, if you like, is less. So it would be less pressure. Well, this one confused me, actually. I had to double check this one. Now tank A is the same as before, but it's just on a table. And the other tank is exactly the same as tank A, except it's on the floor. Just going to have one last look for my favourite liquid while you think about that. I've got like 5 seconds. 4, 3, yes! Found it. 2, 1. Yeah, I have given an answer, but it could be a different answer, really. I've said the same, but, excuse me, that was me peeling the label off my favourite liquid. Yeah, I've said the same. Because we know that we've just looked at the equation and it only talks about depth and density, and neither of those things have changed in the tank, so it must be the same. But the equation that we're looking at is for the change of pressure in a liquid. But the pressure in a liquid does actually also depend, like if you're under the sea or whatever, the amount of pressure that you experience does also depend on the air above you, right? Because there are loads of air particles pushing down on the ocean. So technically speaking, in this scenario, the tank on the floor, there's a tiny little bit of extra air pushing down on that water. I mean, obviously not really, like there isn't really a difference in air pressure between like up here and down here, but there is technically a tiny bit, so be really careful. We're looking at the equation for the difference in pressure between like the surface of the water and 5 meters down or 10 meters down or 15 meters down. But the overall pressure that something experiences does also depend on how many air particles are pushing down on it. Is that okay? Yeah? So obviously the pressure difference between 2 meters down and 5 meters down only depends on the density of the liquid and how deep you go, because you're not changing the amount of air above it. But if you were 2 meters below the ocean and suddenly all the air got sucked out of Earth, that would definitely affect how much pressure was pushing down. I'm just gonna move on. Hopefully that's okay. Right, what about this one? We have now increased the tank. The tank is now 1.5 meters high and the tadpole is still at the bottom of the tank. So it's just the same as tank A, except the tadpole's at the bottom of the tank and the tank is now 1.5 meters high. More pressure, less pressure, same amount? The answer is more, because now the tadpole has more water pushing down on it. So yeah, the depth, the height has changed, so it would be more. Whew. And finally, what about this one? The tank is still 1.5 meters, but now the tadpole is floating quite near the surface of the tank. 3, 2, 1. It would be experiencing less pressure because the depth is less, right? It doesn't matter what the water is doing underneath it. We're just looking at the height or the depth it is below the water surface. All right. And finally, it's my favourite liquid, treacle. If you swapped out the water for treacle, would the tadpole be experiencing more pressure or less pressure or the same amount of pressure? Oops, sorry. Have you got this one? It would be experiencing more pressure because treacle is denser than water. And it makes sense, doesn't it? If pressure is caused by particles like bashing against you, then treacle, it's my favourite liquid, is golden syrup, because I just love how it behaves. It's so beautiful. You can tell that golden syrup is much denser. Its particles are closer together than water, because an air bubble takes absolutely ages to push up through the treacle. You'd say that it's more viscous, great physics word. If a liquid's more viscous, it means it's kind of thicker, gloopier, denser. So yes, the more particles, the closer together the particles are, the more particles pushing down on you. So that air bubble is experiencing more pressure than an air bubble in, say, water would. Right, let's do the activity. It didn't work yesterday on Facebook, however many times I tried it, so that's always a good start. What you need to do is get a piece of tissue or kitchen roll, get as small a glass as you can find and as deep a container of water as you can find. So I hope you're not allergic to nuts, because I'm using this tub that I usually keep nuts in because it's clear and it's very deep. I don't know whether it was its narrowness that was stopping this working though. What you do is, I think it'll help if you slightly, only very slightly dampen the tissue, and you have to sort of stick it inside your wine glass or whatever glass you're using so that it doesn't, there we go, thank goodness for water being sticky, so that it doesn't peep out of the glass. You've got to be able to hold the glass upside down and the tissue not fall out, and you can just feel that this isn't going to work again. And yeah, you've got to have it not poking out, because what you do is you just push the glass face down so it hits the water like dead on, and just push it down as far as you can go and see what you see and see what you feel. Are you ready? You love it. The adults in your houses absolutely love it when I fail. They're always like, oh, it's so great that you model that things don't go right first time. Yeah, sometimes I think I'd like to be one of those Instagram channels where stuff does work, because I've secretly used a glue gun. Anyway, I'm putting it dead in and see what happens. Oh, is that water going to overflow? Oh my goodness me. Oh, look at that. Okay, wow, cool. So what has happened? Oh, YouTube, you're so good to me. Can you see that tissue is staying dry? And I would say push right to the bottom. I'm not going to do that because I'm going to make a terrible mess and get Lego Story Show for tomorrow's YouTube lesson wet. But look, the tissue stays dry, and you should feel a push. And if you've got room to push right down, you should feel the push increasing the further down you get. Right, let's bring that back up again. Oh, yeah, come on, so cool. So what is happening there? Why does that happen? What is the push that you are feeling? So why does the tissue stay dry is my first question. Why does the tissue stay dry? And what is that push that you're feeling? Why are you experiencing a push? What's causing the push? That's really beautiful, isn't it? This is what they used to do. We've done a whole Lego story show about deep sea diving just because I wanted to do this activity, but it's really interesting. People just used to put themselves in massive cups, basically. Right. So we've done that. Yeah, now you're probably saying, like in the all ages lesson, they were saying, oh, there's an air bubble trapped inside. Yes, that is true. You trap air particles inside the glass, and obviously there's air pressure then inside the glass. Air particles are pushing against the glass and pushing against the water, which keeps the tissue dry because the water can't get into the glass. So that's why the tissue stays dry, because of this air bubble. But what is the push that you are feeling? What is that push? It's actually sort of quite complicated, isn't it, if you really think about it? What is pushing? Well, the air particles are getting squashed, okay? If you could push it really deep down, you would see the water level getting kind of higher and higher, because as you push the glass down, you could try it in the bath later, don't put glass in though. Yeah, the pressure, the water pressure is getting more and more and more the deeper down the glass gets. So water is pushing itself further and further into the glass, and the air particles are getting squished and squished and squished, closer and closer together. The air is getting denser in there. So the push that you're feeling is the water. It's the water pushing on the glass and pushing on the air. So how do we draw arrows? Let's just get onto that. To show pressure in a liquid, that's the next question that I've written to myself. You might well see this in a diagram in an exam. This is supposed to be, I'll tell you what. Let's just pretend that we've drawn the ocean. I'll not pretend that we've drawn it. I will actually draw we've got an orange ocean here. Oh no, it's the apocalypse, don't worry about it. Here's a dam. Someone has dammed up the ocean because it's made of horrible poison, because it's the future. And let's say that we've got a fish here which has evolved to survive the horrible poison. How you would draw diagrams to show the pressure at different levels is the bigger the arrow, the more the pressure. We've done this before, like the more force acting. So if you were going to draw the pressure or the force pushing on this dam, then the top arrow would show that the pressure is quite small arrow, and then as you went along, the pressure would get bigger and bigger and bigger and bigger, right? So if there's two evolved mutant about to rule the world fish, the one that was higher would have smaller arrows pushing on it because it's experiencing less pressure, and the fish that's down here would have larger arrows acting on it. And actually, I suppose really, the arrows on the bottom would be bigger. This is exaggerated. And the arrows on the top would be smaller because obviously the bottom of the fish is lower down. Right, I've got some questions for you. So I've got two scenarios here. One of them is very heavily based on an actual past paper IGCSE question, which I will link you to in my Facebook group so that you can do it for homework. It's quite challenging, so I thought we'll do it here. You probably won't get this question right, and then you'll get the question right when you try it for homework. A little note. You have to change something on your sheet, please. If you've been to my Facebook group and downloaded the sheet, I've told you that the density of seawater is like 30,000 or something. It's not, it's 1,000. Can you do this now or you'll get the wrong answer? I've said the density of seawater, can you change whatever you've got on your sheet? That number should be 1,000 kilograms per metre cubed, okay? The density of seawater is 1,000 kilograms per metre cubed. If you haven't got the sheet, you're totally fine because it's all right on here. Okay, right, you ready? Off we go. So, I don't know if you noticed, the Theatre of Science mascot is Wormy, and quite a while ago we did have this storyline that Wormy had 2 children, and we haven't heard from them for ages. Well, it turns out that Wormy's daughter Wilhelmina is taking a gap year and she's gone exploring around a kitchen. So she's dived to the bottom of a bottle of golden syrup. If the syrup is 25 centimetres deep, with a density of 1,400 kilograms per metres cubed, how much pressure is acting on Wilhelmina? I've said, can you assume, just to make the equation easier, assume the pressure at the top of the syrup is 0, please. Obviously it's not, because there would be air particles pushing down, but let's just say that it's 0. How much pressure is acting on her? And question 2, the bottom of a boat is on the surface of the ocean, experiencing a pressure of 500 pascals. Do you remember from a couple of lessons ago how you measure pressure in pascals? Don't worry if you don't, you can go back to it later. Weight is added to the boat, and the boat moves down, so now the bottom of the boat is 2 meters below the surface. If the density of seawater is 1,000 kilograms per meter cubed, what is the new pressure acting on the bottom of the ship? And I've told you here, I don't think you actually have to remember this anymore, but it should be in your head really, that little g is 9.8 newtons per kilogram. And here's your equation. The change in pressure equals density times little g times the change in height. Little public service announcement that if for the first one you've got the answer 343,000, that is not correct. What have you done? 343,000 is not the answer to the first one. You're close. You probably get a mark, but you've made a mistake. There's something you've forgotten to do. Similarly, if for the second one you have an answer of 19,600, that is also not the correct answer. The answer to the second one is not 19,600. You have also forgotten to do something, but you're close. I'll give you, 20 seconds. Let's set the, I'll set the golden syrup timer on. Okay, well, let's go through it. Like I say, I was sort of almost expecting / possibly even hoping that you would get this wrong, so then you'll definitely remember how to do it when I give you the past exam questions. Okay, first one. Wilhelmina's taking a gap year, blah, blah, blah. She dives down 25 centimetres deep into some golden syrup, and you've got the density of golden syrup. How much pressure acts on her? Check your units, first of all, please. We need H to be in metres, don't we? If you remember from last lesson, or a couple of lessons ago, do you remember this? Can you remember the equation for pressure in solids? If you've just got like a high-heeled shoe, say, pressing down on a wooden floor, what's the equation for how much pressure that high-heeled shoe is putting? Oh, I'm writing backwards. Did I write backwards before? Oh, I'm really sorry. Did I write? I blooming did, didn't I? God, just keep doing that. I'm so sorry. It's because when I'm teaching on Facebook, you know, I have to flip it, and I don't when I'm on YouTube. So pressure equals force divided by area. You remember that? I'm getting new pens for Christmas. Pressure is force divided by area. Force is measured in newtons, and area is measured in meters squared. So the force would be like the weight of the person and the area of the high-heeled shoe, okay? This, newtons per metre square, we just call that the Pascal, and that's how you measure pressure. But you can't just use centimetres in an equation and then say, oh, it's blah, blah, blah Pascals, because Pascals use metres. So you had to have changed these centimetres into metres. So you divide by 100. So you get pressure equals density times little g times change in height. So the density is 1,400 kilograms per metre cubed times 9.8 newtons per kilogram times 0.25 metres. And that gives you 3,430 pascals. Or you could have said newtons per metre squared and then just changed it. And the second one, the bottom of a boat is on the surface of the ocean experiencing a pressure of 500 pascals. Weight is added, the boat moves down, so you've got a change in depth. And you've got the density of seawater. So this time we don't need to do any converting. So the pressure at the bottom is the density of the seawater times G times the change in height. Well, actually, I've corrected myself. That's the change in pressure, isn't it? The difference between the pressure at the surface and the pressure 2 metres down. So we'll just plug in the numbers. 1,000 kilograms per metre cubed times 9.8 newtons per kilogram times 2. And that gives you 196,000 pascals. But that's not the right answer, is it? Why not? Well, it's asking you what the new pressure is acting on the bottom of the ship. What's the complete total new pressure? Well, there was already some pressure at the top, like the atmospheric pressure. This 500 PA is the pressure, if the boat's at the surface, this must be the pressure of all the air pushing down. And that's still pushing down. So you've worked out the pressure difference between the surface and 2 metres, but you need to, for the overall pressure, you need to add on the pressure that was there to start with. So 196,000 pascals plus 500 pascals equals 20,100 pascals. Whew. Very well done if you got that. Like I say, if you didn't get that, that's kind of what I was expecting. The IGCSE question that I'm going to give you is actually a little bit kinder than this. It gives you the answer and it says, show how we got this answer, basically. So if you get the wrong answer, you know it's wrong and you can go back and keep trying again, which is much kinder than what I just did. Can we quickly, I know I feel like I sort of bang on about this a lot, but can we look at how you would have known roughly whether you'd have got the right answer, even if you couldn't check it? So the writing forwards, the change in pressure equals density. Please, can you just write out this equation if you want with me and look at what the units are? Density times little g times, I'm just going to write height because changing doesn't matter. What are the units of density? What are the units of density? It's sort of the amount of stuff per cubic metre. So the units of density, I'm really sorry if you can't see this, are the amount of kilograms per, in fact I'll draw it like this, it makes it easier to see. The amount of kilograms per metre cubed. Is that okay? We did density fairly recently. In fact, you can see here what the equation for density is, can't you? Density equals mass, which is measured in kilograms, divided by volume, which is measured in metre cubed. So that's the unit of density, kilograms per metre cubed. And then we're timesing that by little g. So let's look at the units for little g. Newtons per kilogram. You okay with me just using this dividing line? This means per. And height is obviously just measured in meters. Phew. So if this is what all our units are doing on this side, the units should be the same on the other side. So let's have a look if they are. So we've got kilograms on the top here, and we've got kilograms on the bottom. So we can cancel that out. I'm worried I might be doing that physics teacher thing that I got when I was a kid, just like numbers, 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 numbers there. Do you see now? Do you understand? And I was like, no, and I'm never doing this subject ever again. Luckily I got over it. So the kilograms have cancelled out. We've got 1 metre on the top, and we've got a metre cubed down here. So we can cancel out that metre and just cancel out one of these metres. So that turns into metres squared. So what have we got left on this side? We've got the units newtons per, gasp, metre squared. Which is right, isn't it? That's what pressure is measured in, newtons per metre squared, but another way of saying that is pascals. So if you're ever not sure of your answer, you think you might have rearranged the equation wrong or whatever, check all the units of your equation and see if the right thing pops out, and you've probably got it right. Okay, very quickly then, let's go back to our water activity, because you should totally do this at home when you get a minute, if you've ever got a plastic bottle. How the diagram would change if we used this enormous bottle. I'm hoping that now you can see that, well, if the viscosity or the density, the same thing, of the liquid is the same, so if it's still using water, and the height of the holes is the same, so the depth is the same, and they're both on planet Earth, they will be the same. Try it. Do it with a thinner bottle and a thicker bottle if you've got them, and see the pressure difference. There shouldn't be any pressure difference because you haven't changed the height or little g or density. And finally then, just to see how much you've taken in this lesson, you are planning a journey to the bottom of a strange planet's ocean. The pressure on you will depend on, how many of these is it? You're going to the bottom of a strange planet's ocean. What does the pressure on you, what is it affected by? Is it the ocean's density, the ocean's mass, how deep you go, the planet's atmosphere, the volume of the ocean, the planet's acceleration due to gravity, or your weight? How many of those is it? This seems like a good situation to use the golden syrup timer on. So when this bubble's got to the top, then I'll tell you the answer. I think we might have invented a new way of measuring time. Okay, it's hit. Well, the answer is, going on that change in pressure equation that we've been looking at, change in pressure is density times little g times height. You might have said the ocean's density, you'd be correct. How deep you go, definitely. And the planet's acceleration due to gravity, which is little g, how much gravity is pulling on you. But the overall pressure on you, that's the equation for the change in pressure in a liquid, but the overall pressure on you will depend on the planet's atmosphere as well. So very well done if you got that in. If the planet's atmosphere is not very much, then that would lessen the pressure. But yeah, okay. Right. Good. Lesson ends. I'm going to flip you back round. So we've got one more IGCSE physics lesson if you're watching this live before I take a break for Christmas to raise my children. And in fact, this one's at a different time next week, isn't it? Sorry, I should have been more organised and definitely told you that. It's okay because I'm on my Facebook page because I'm going to say hello to people. Next week, I have to finish teaching on... Oh, wait. Sorry, it's not you. I don't think it's you. Oh my goodness, it's just a disaster. Next week, your lesson is fine. Your lesson is totally fine. It's the all ages lot. that I'm having to change the time of, because I'm free on Wednesdays and it's Wednesday. This is fine. It's the Thursday people that are getting messed around. Okay, well, I'm just going to go on my Facebook page and say hello to you, see if anyone's left me any messages. If you want to support me, you can. You know this. Nobody turns up new to like lesson 4, module 5 or whatever of IGCSE physics. But if you have, please go to my About section and look at my link to my coffee page, where you can support me if you want to. You can chip into my wages, and I will send you nice things to say thank you very much, because I could not do this job without you, and this is clearly the best job ever. Like, I loved classroom teaching, but I like this more. Has anyone said hello? I don't think they have. I think we're all free to go. Facebook's gone a bit weird. But I think we can all just go about our business, and I will see you next week. I can see people are watching, so hello, and thank you for coming. Very soon, really soon, over the Christmas holidays, a new website will go up, which will have all the printouts and all the links to all the videos in one place, and you won't need Facebook at all. So if you're watching this and you're not on Facebook, happy days are coming to us all. Right, thank you for coming, you lot. I'll see you next week for our last IGCSE physics lesson. If you come to my all ages lesson, there's another one next week of those as well, but there's no Lego Storytime show next week because, like I say, I'm parenting. So the last Lego Storytime show on YouTube is tomorrow at 10:30. It's on Reindeer. Thank you for coming. I'll see you all soon. Bye.